we're just going to finish up that problem we were looking at yesterday. With carbonate. And so, in the first step, carbonate's a base. It's going to hydrolyze water to form bicarbonate and hydroxide. So we started off with a point, what was it, 0.1 molar, 0 molar, and 0 molar. And, what was it? We lost about 9.5% or 5.5%. Is that right? No, 5.5%. And so, what did it come out to here? It came out to point. Zero 955. Okay, thank you. 0.0955. Actually, you know, according to the rules for sig figs, this should round to the 10th place. So it would round to 0.1, but you know, we're going to carry extra digits, otherwise it doesn't look like anything changed. Over here, this is going to be 0.0045. 0. Is that right? No, 45. Just leave it at that. Let's carry an extra 0. 0.0045. 0. We'll just carry some extra digits. At the end, we'll round things off. All right, so after the first step, we saw that we had some hydrolysis of the carbonate. Carbonate's a base. We produced some hydroxide. But it turns out this is a base solution, and there are other hydroxide producers here. And one of them is bicarbonate. Bicarbonate is also a base. And we could have understood this because carbonate's a dibasic base. It's capable of accepting 2 protons. And so in the second step, we took our bicarbonate and hydrolyzed water. Now, bicarbonate hydrolyzing water is going to form carbonic acid, H2CO3, and hydroxide. So this is also going to produce some hydroxide here. And let's take a look at the Kb values here. The Kb, what was the Kb for the first hydrolysis? Did we calculate? Like 2.3? Give me one more digit. 2.3. Was it 2.2 something? Well, it's kind of small. Then over here we go to the next one. This is going to have a Kb as well. This is going to be the Kb for bicarbonate. This was the Kb for carbonate here. The Kb for carbonate is what we call Kb1 for carbonate. Then the Kb for bicarbonate would be equal to Kb2 for carbonate. Kb2 for carbonate is Kb for bicarbonate. This is the second step, being in a dibasic base. And so that's something we'll see. Over here, we'll do is, this is the end of the line for the carbonate. The carbonate stops here. However, this one is going to be carried down into the next step here. And so this is 0.00450 molar. Water is a liquid. We don't have any, carbonic acid. We assume that nothing's collided yet. But we do have some hydroxide, and that's going to inhibit the amount of hydroxide that's produced because we already have a lot of product here. And so what was the equilibrium for this? This was 0.004. What did we get? 50. Etc. In fact, I carried a whole bunch of extra digits here because the changes were so small. This is 0.00450. What was the carbonic acid concentration? Here. did we solve for this one? Do you have this in your notes or not?
It was 2.72 times 10 to the negative.
Times 10 to the negative 8 molar. All right. Did this step produce much additional hydroxide? No, not really. It didn't. It just added a tiny bit of hydroxide here. And so from step 1, we end up with this. From step 2, we add a little bit, x, which is 10 to the minus 8. We add 10 to the minus 8, 7 zeros, and 2. So it's not much additional hydroxide here. But there is one more hydroxide contributor, and what is that? Water. Because carbonic acid, this is not a hydroxide. This is only an acid. This is not amphoteric. You can't go both ways. And so that's our step 3. And so step 3 is going to be water, autoionization, or water hydrolysis. This is going to produce hydronium and hydroxide. Now, what we do is we'll just assume that no water has hydrolyzed yet, so there should be 0 molar hydronium. And normally we produce hydronium and hydroxide in equal molar proportions, but we have to consider we already have a whole bunch of hydroxide present. And so this is going to go down into the next step. So in the next step, we'll have 450 molar here, and then we're going to see how much additional hydroxide we're going to add to this. And so the additional hydroxide is going to be plus X molar and plus X molar. A lot of people think that X should be 10 to the minus 7. The X is 10 to the minus 7 because autoionization of water produces 10 to the minus 7 molar hydronium and 10 to the minus 7 molar hydroxide, but that's not the case. It's not the case because we have a whole bunch of hydroxide here to begin with, and so we don't need nearly as much as 10 to the minus 7 molar. And so we have to calculate how much that is, and so this is going to be 0.00450 plus X here. Okay, then we'll solve this using KW. This is 1.0 times 10 to the minus 14, which is hydronium times hydroxide, which is going to equal X times 0.00450 plus X. Here, even though the quadratic's easy, I'm going to try the simplifying assumption because, you know, when I look at the K value, it's 10 to the minus 14, which is very small. And so we expect very little product anyway. And so let's go ahead and make the simplifying assumption that is X is much smaller than 0.0045. So that's going to simplify it to 0.00450. Now this X doesn't drop out, but this X does drop out. And then solve for X. What do we get for X here? So I have 1 times 10 to the minus 14 divided by 0.045. I get 2.22 times 10 to the minus 12 molar. 3, 6, 9, 12. Yeah. You know, here, if we look at the percent change, you know, change is so small. Change is 10 to the minus 12. The initial is 10 to the minus 3, let's say, times 10 squared. So this is going to give us 10 to the minus 7% change. And so roughly about a 10 to the minus 7% change means that the simplifying assumption, you could have high confidence in the simplifying assumption. I mean, if we did this using the quadratic, we'd get the same answer, you know, with that kind of percent change there. And so we end up with this. We end up with 2.22 times 10 to the minus 12 molar here, and about 0.00450. You know, plus 10 to the minus 12 would be 11 zeros. And so that's really not going to have an impact on this here. Normally I would write it all out, since I don't have these numbers here, but I think no one wrote the complete numbers out, so leave it like this. All right, and so you could see that, you know, most of the hydroxide was produced in step 1, and pretty much a negligible amount was added in step 2, and an even more negligible amount was added in step 3. And so this is a typical scenario. When you have something like a dibasic base or tribasic base or diprotic acid or triprotic acid, most of the hydronium is produced in step 1. There are exceptions. There are exceptions, you know, if step 2 had a significant K value. So if step 2's K value was somewhat large, and somewhat large would be like 10 to the minus 2. If step 2 had a K value of 10 to the minus 2 or bigger, then I'd worry, because that K value tells me that there should be a significant amount of hydroxide produced. But this was like, as I recall, 10 to the minus 4. This is 10 to the minus 4. That's not really going to be significant. And this K value is 10 to the minus 14, which is very small. So if I was interested in pH, would I do all 3 steps? No, I would probably just do step 1, possibly step 2. The only time I'd do step 2 is if K for step 2 is fairly large, on the order of 10 to the minus 2. And 10 to the minus 2 is still small, but large in relation to the calculation. And so here, we could have stopped here, got the pOH from this, and calculated the pH, because as you see, if we go through all the steps, we're going to get the same pH. Okay, now what we're doing is we're doing this in sequence. When we're doing this in sequence, what that means is this. I don't add these up. You know, what I do is after step 1, I see how much additional hydroxide I get. And so this is the hydroxide from step 1. I add hydroxide from step 2. So here's the total. And then I go over here. And this is the total hydroxide from steps 1 and 2. And then I see how much additional hydroxide I get in step 3. Now, what we want to do is we want to double check. So we double check step 1, is that correct? It worked out. How about step 2? Did we double check step 2? And it worked? Yeah? All right. We have to be very careful in our double check, because what happens is this. What happens is we have to worry about Le Chatelier's principle, and that is, if we do step 1 and step 2 screws up step 1, because it should, step 2 should change what we have for the equilibrium concentration. So we take a system at equilibrium and change it. For example, here we're going to decrease the amount of bicarbonate and increase the amount of hydroxide. That's going to screw up the equilibrium here, right? And so if we change it, that is, if step 2 perturbs the equilibrium in step 1, then we run into the problem of Le Chatelier's principle, where things are changed. And the same thing here. But when I look at the bicarbonate, did the bicarbonate change significantly? No, it was a negligible change. And so what that means is this bicarbonate value satisfies the equilibrium for both step 1 and step 2. Essentially. And now the hydroxide changed here, but it's going to change one more time. The hydroxide changed here again. And so this hydroxide, does it satisfy the equilibrium conditions for all 3? And the answer is, yeah, if you look at the number, it satisfies the equilibrium for all 3. And so what we have is we have this equilibrium value of hydroxide would double check out step 1, step 2, and we didn't do this. Let me double check this one here. That is, I'm just going to take 2.22 times 10 to the minus 12. Times 0.0045. And I get 1 times 10 to the negative 56, 3, 6, 12, 13, 14. And so K checks out. It comes out to 1.0 times 10 to the minus 14. So we're good. Double check. All right. And so what we see here is this. What we're going to do is we're going to see what the solution inventory is. If we're doing the solution inventory is this. It's trying to figure out what species are present in the solution. And so if I had a beaker, and this beaker is labeled 0.1 molar sodium bicarbonate, what species do I have present and in what concentration? And so if I'm looking at this, we'll just list the species. The first species will be the sodium ion. That just comes from this being a strong electrolyte. The sodium ion is going to be 0.2 molar. For every mole of sodium carbonate, you get 2 moles of sodium. Okay, then the next species we'll look at is carbonate. Carbonate just about 4.5% ionized. 95% remains. And so the carbonate is going to be quite abundant at 0.0955. I carry extra digits, otherwise sometimes these changes can be small. It's hard to see. So normally I carry extra digits. You can round these at the end. And then we have bicarbonate. Bicarbonate is 0.00450. Actually, it's just slightly less than 0.00450. Because we're going to lose a little bit in this step, minus X. So it's just slightly less than that. Okay, so that's where the bicarbonate. Carbonic acid ends here. You're going to have a little bit of carbonic acid, 2.72 times 10 to the minus 8 molar. Carbonic acid, 2.72 times 10 to the minus 8 molar. Hydroxide doesn't end here. Hydroxide continues on into this step. So hydroxide ends here. So the total hydroxide, adding up all 3 steps, is going to be 0.00450 molar. It's just going to be a hair above that. And so the bicarbonate will be a hair below, hydroxide will be a hair above. And we have one more species. We have hydronium in here. We're going to have hydronium in a basic solution. We're always going to have hydronium and hydroxide present in any solution. It's just that in the basic solution, the hydroxide should be greater than the hydronium concentration, and that it is. There's barely any hydronium. And the hydronium we can't get rid of completely because the collisions never stop. And so hydronium is going to be 2.22 times 10 to the minus 12 molar. All right, now when we do the pH, that was the original question, we'll just do it from the pOH. And so first we'll take the pOH. pOH would be the native log of 0.00450. That would be the total hydroxide concentration. So let's figure that out here. 0.0045 log base 10. Change this. Somebody have it? Okay, how weird. My log base 10 changed for a moment. It was something else. Okay, now it's back. 0.0045 log. 2.346. And therefore the pH would be 14 minus that. 11.653. So my pH is 11.653. This is what we call our inventory here. This would be all listing the species present. Based on, here again, we ignore activities and this kind of stuff. All right, what we just did here, and what we did with the other one, is this. This is called a stepwise. Well, I call it stepwise. You know, the method here is stepwise. And so a lot of these types of multiple equilibria, we can just do it in steps. We start off with the biggest K. And so stepwise, start with the biggest K and then work your way down as far as ordering goes. Start with biggest K and then go smaller. Not everything works using the stepwise method. So let's look at what we're doing. 1.0 times 10 to the minus 8 molar HCN. Is that the problem we left off with last time? Yeah. So let's go back to this problem and work on this one. Well, HCN is an acid. And so if we have acid in water, we look for all the hydronium ion contributors. This is a monoprotic acid. And so we're only going to be concerned with Ka. Ka will produce hydronium, and Kw will produce hydronium. And so it looks like a two-step deal that we do. You know, we start off with the biggest K. What was the Ka? Ka was like 10 to the minus 11, 10 to the minus 10. What was it? What will contribute more hydronium, Ka or Kw? Well, it depends. Which one was bigger? Ka, did anybody write down the Ka value for HCN? No. All right, let's go back and take a look at the Ka for HCN. K values are in appendix D. Also, there are some in the chapter, but appendix D is much more comprehensive. When we have a table like appendix D, Ka values, it's always a good idea to take a look at the range of the K values. You know? Like the smallest. What was the smallest K value? Biggest. All right. So if we look at the range of K, 10 to the minus 5, 10 to the minus 10 arsenate acid. The biggest K value that we see here. The smallest K value. Hydrosulfuric H2S, the HS with minus ion, 10 to the minus 19. Very small. Minus 19. Some of the biggest, like trichloroacetic acid, is 3 times 10 to the minus 1. What's going on with this? Sulfuric. What's wrong with the K value there? H2SeO4, selenic acid. Something wrong with that. Actually, it's not. We kind of assume it's infinity, but it's not really infinity. We just say it's very large. And so that's why. The biggest are very large, or very, and the smallest are, 10 to the minus 19. So there's a huge range in K values, which means there's a huge range in acid strength here. And so the strong acids are going to have very large K values, but some of these, like trichloroacetic acid, borderline strong acid. Even though 0.3 doesn't seem all that big, it's pretty big. And so the percent ionization should be kind of high. 0% reaction, percent hydrolysis. HCN is pretty weak. HCN is 6.2 times 10 to the minus 10. It's a pretty weak acid. So this is 10 to the minus 10. KW is 10 to the minus 14. And so what we do in the stepwise, when we turn to stepwise, we do the bigger K first, whether it's KW or KA. Just pick the biggest K. And it depends on your acid. Sometimes you could have acids with a K value less than 10 to the minus 14. If you have an acid with a K value less than 10 to the minus 14, then you got to do KW first. And water is going to be the most significant contributor of hydronium. But in this case, HCN should still be the most significant contributor of hydronium, and then the next most significant contributor will be KW here, so the smaller K. So we start off with HCN here. HCN plus water, acid and water is going to give us hydronium and cyanide. We have our Ka. Ka equals 6.2 hydrocyanic acid, 6.2 times 10 to the minus 10. And this is going to equal the hydronium ion concentration times the cyanide concentration divided by the HCN. Water is pure liquids. Don't include that in there. And so initial, we have 1.0 times 10 to the minus 8 molar. Nothing. And we're going to assume nothing's happened yet. And so now we're going to let the collisions between HCN and water take place. And so we're going to get minus X molar, plus X molar, plus X molar. So at equilibrium, we're going to get 1.0 times 10 to the minus 8 minus X, and then X, and X. So this is going to go to X times X is X squared divided by 1.0 times 10 to the minus 8 minus X. So, although this doesn't look hard to get in a quadratic form, just try the simplifying assumption. See if that works. Simplifying assumption, we're going to say X is much smaller than 1 times 10 to the minus 8. If that's the case, then this should simplify into X squared over 1.0 times 10 to the minus 8. Even though 1.0 times 10 to the minus 8 is a very small number, go ahead and try it. And so this gives us an X equal to okay, so 6.2 times 10. 10 to the minus 10 times 1 times 10 to the minus 8. I'm going to take the square root of that. 2.48 times 10 to the 3, 6, 7, 9 times 10 to the minus 9. And so what we'll do is we'll do a percent change for this. Percent change will be this over the initial. So it's going to be equal to 2.48 times 10 to the minus 9 divided by 1.0 times 10 to the minus 8 times 100%. So divided by 1 times 10 to the minus 8 times 100. It comes out to 24.89%. 24.89% is not acceptable. So, but it didn't take, we didn't waste too much time. And so it's worth trying. So we can't use it. And so we'll just have to get it into quadratic form. So let's go ahead and get this into quadratic form. So this is going to be x squared. Squared plus 6.2 times 10 to the minus 10x minus 1.0 times 10 to the minus 8 equal to 0. So we get a quadratic form, and let's see, I should still have the website here. Math is fun or something. Unless I closed it. Did I close it? Oh, here it is. All right, so A is 1, B is 6.2 times 10 to the minus 10, and C is negative 1 times 10 to the minus 8, so negative 1 times 10 to the minus 8. So we got x1, x2 here. x1 is point, well, x2, it can't be x2.
It's bigger than the last x.
Hmm?
Isn't that bigger than the last x?
Bigger than what?
The last x we saw.
Yeah.
Bigger percent change.
I know, but this x here is based on an assumption.
Oh, I see.
This x, we don't have any assumption. We know it's a big change, right? We know it's a big change. And so we don't have to worry about justifying anything because we didn't do any assumptions here. We just solved it outright. So this is going to be quadruple 0, 9, 9, 9. And so you could see that the simplifying assumption is way off, I think, unless I messed up the calculation here. Unless I messed up the calculation. Did I mess up the calculation? I must have messed up the calculation because if we look at this here, that x value is going to make this go negative. And we can't have a negative molarity. And so I must have messed up somewhere. Let's see where I messed up. Oh, I see where I messed up. And so 6.2 times 10 to the minus 10 is okay, but 1.0 times 10 to the minus 8 times 6.2 times 10 to the minus 10 is not 1 times 10 to the minus 8, right? This number is wrong. Messed up. It should be 6.2 times 10 to the minus 18. So this is 6.2 times 10 to the minus 18. That's where it was. And so this C is 6.2 times 10 to the minus 18. Let's solve this. Yeah. Well, automatically we can eliminate the negative. And so this is times 10 to the minus 9. 2.19 times 10 to the minus 9. 2.19 times 10 to the minus 9. All right, so I have 1.0 times 10 to the minus 8 minus, I'm going to make that 10 to the minus 8 as well. That would be 0.219. 0.219 times 10 to the minus 8. And so this is going to give me 0.781 times 10 to the minus 8 molar.
That's almost the same as the first calculation.
Yeah, it's pretty close. With the simplifying assumption, it was 2.48. With solving the quadratic, it's 2.19, so it's not terrible. But there is a, if you were to calculate the percent error, what would the percent error be? Well, the percent error would be about 0.3 over 2. 0.3 over 2 would be times 5. 0.3 times 5 would be 1.5. It would be about like 1.5%, right? 1.5% error, or no, am I right?
15%.
Yeah, not 1.5, 15% error. 15% error, okay? And so, yeah, do the quadratic. And so x is over here is 2.19 times 10 to the minus 9 molar. 2.19 times 10 to the minus 9. So we don't stop here because water can also contribute hydronium. And so we have to consider that. And cyanide, would cyanide contribute hydronium? No, cyanide doesn't contribute hydronium, but you know what cyanide is. Cyanide's a base. So should we worry about cyanide contributing hydroxide to this? I mean, shouldn't cyanide contribute hydroxide to this? See, we're producing, okay, we're going to produce some hydronium. We got some cyanide here, but cyanide can hydrolyze water to form hydroxide. So take a look at that over here. And so cyanide can hydrolyze water to produce HCN and hydroxide. And so maybe I should, if the cyanide hydrolyzes water to produce some hydroxide, that can neutralize some of the hydronium I just produced, correct? And so maybe I should do this before I do the water. Should I do this before I do the water? No, I wouldn't bother doing this. Why? Would I not bother doing this? Because I already did this. Can you see I already did this? This is step one. This is step one. You could do. We could have done step one in this way. In step one, in this way, we would. But anyway, this is the equilibrium between cyanide and hydrogen cyanide or hydrocyanic acid in terms of pOH. So I wouldn't do that. In other words, we only look in acid. This is an acid solution. We only look for hydronium producers. So cyanide is not a hydronium producer. So ignore that. But water is a hydronium ion producer. So let's go to water next. Water can produce hydronium by autoionization and hydroxide. Normally water produces 1 times 10 to the minus 7 molar, but it's not in this case. It's not going to produce 1 times 10 to the minus 7 molar hydronium because of the presence of some initial. In chapter 16, I call this kind of Le Chatelier's, increasing this is going to inhibit the forward reaction. This is 0 molar. In chapter 17, we call this the common ion. And so what happens is step 2 has a common ion with step 1, and the common ion is hydronium. And the common ion has to be shown here. All right, and so the change here, well, water molecules, we can't stop those from colliding. They're going to collide and produce some additional hydronium as well as hydroxide. And so we're going to get 2.19 plus X molar and X molar here. And so Kw, which will equal the hydronium times the hydroxide ion concentration, is going to equal 2.19 plus x times x. 2.19 times 10 to the minus 9 times 10 to the minus 9 times 10 to the minus 9. Oh, we're going to just go ahead and try the simplifying assumption. So we're going to assume that x is much smaller than 2.19 times 10 to the minus 9. So this is just going to simplify it into 2.19 times 10 to the minus 9. And then this x stays because everything's significant compared to 0. Which we're doing here. Compared to 0, everything's significant. And so here, let's go with this and see what we end up getting. KW is a number you should memorize, 1.0 times 10 to the minus 14 at 25 degrees C. So I have 1 times 10 to the negative 14 divided by 2.19 times 10 to the minus 9. 2.19 times 10 to the minus 9. I get this. I get x equals 5 zeros. 1, 2, 3, 4, 5, 4, 5, 6. Well, let's go ahead and calculate the percent change. Percent change would be the change x over the original 2.19 times 10 to the minus 9. So let's divided by 2.19 times 10 to the minus 9. With that times 100. Percent change comes out to 208,502%. This obviously, the simplifying assumption failed here. Unfortunately, fail. A couple of reasons it failed. One, KW is very small. Two, we have a very small initial. You know, the bigger the initial concentration here, the more likely it is to succeed. And the smaller the K, the more likely it is to succeed. In this chapter, Petrucci gives you a ratio, K over the concentration over the K, to indicate when the simplifying assumption is likely to work and when it's likely to fail, but we're not going to look at it now. And so it failed, so I need to get this into quadratic form, but fortunately this one's easy to get into quadratic form. X squared plus 2.19 times 10 to the minus 9x minus 1.0 times 10 to the minus 14 is equal to 0. So let's go ahead and plug in A. Our B is 2.19 times 10 to the minus 9. And our C is negative 1 times 10 to the minus 14. Solve that. Okay, obviously it can't be x2 because it's negative, so it's going to be x1. And this is times 10 to the minus 8. 9.89 times 10 to the minus 8. So x equals 9.89 times 10 to the minus 8. And so we don't have to justify this because we went ahead and calculated the math out. And so over here, this is going to be 2.19 times 10 to the minus 9. I'll just leave it at 10 to the minus 9. 2.19 times 10 to the minus 9. I'm going to convert that into 10 to the minus 9. And so that would be 98.9 times 10 to the minus 9. And so I would get 101.09 times 10 to the minus 9. Here. And then the hydroxide comes out to 9.89 times 10 to the minus 8. Uh-huh.
So with the other electrolysis of water, the initial concentration of H3O doesn't change the equilibrium?
It does. I mean, if there was, it doesn't change KW at all. KW is the same.
Okay.
Yeah. KW is based on the collisions with the water molecules. Collisions are going to stay the same. What's happening is Le Chatelier's principle. There are two ways to solve this. We could have water at equilibrium, if water is at equilibrium, then it's 10 to the minus 7 and 10 to the minus 7 molar. Right? And so if it's at equilibrium, it's 1.0 times 10 to the minus 7 molar, 1.0 times 10 to the minus 7 molar. And then from step 1, what we're doing is we're adding some additional hydronium to that 2.19 times 10 to the minus 9. And so from the hydrocyanic acid, we're going to go plus 2.19 times 10 to the minus 9 molar, the hydronium. And then this is going to be plus 0 molar. And so what's going to happen here is now this has screwed up the equilibrium, right? This has screwed up the equilibrium. And so it's got to shift to the left, but it doesn't change K. K stays the same. The only thing that would change K is temperature. Temperature changes K, but it doesn't matter what your concentrations are. We can start off with any concentrations we want. It's going to reach the equilibrium. Well, I don't do it as a Le Chatelier's type setup. This is a Le Chatelier's type setup we did in chapter 15, number 40. I like to do the reset. You know, and this is what we're doing here. We reset in step 1, we reset in step 2. What reset means is just assume nothing's happened yet, and then just let it happen. The reason why, like some of those have a very large or very small K value is to reset it, and then figure out the equilibrium afterwards. So let's double check this. Did I double check this? I forgot to double check this. Let me go ahead and double check step 1 to make sure it checks out okay. And so, step 1, 2.19 times 10 to the minus 9 squared. 2.19 times 10 to the minus 9 squared. Divided by 0.781 times 10 to the minus 8. I get 6.14. When I double check the K value, 6.14 times 10 to the minus 3, 6, 9, 10 times 10 to the minus 10. What was the K value? I erased it. What was the K value supposed to be? I wrote about that. I just was the reason.
6.7.
6.7. We're off. Shoot. Was it 6.2? Oh, 6.2. If it's 6.2, we're still off a little bit, but it's probably due to round off. I only carried 1 extra digit here. If I carried more digits, I would get closer. It's important because on a test, sometimes you're off even more, and you don't know, did you make some more significant mistake, or is it just because of rounding? And so this is why I tend to carry a lot of extra digits, so there's one less thing I have to worry about. The reason I wrote 10 to the minus 10, I just did order of magnitude because I didn't know which one I wanted to do first. When we do stepwise, multiple equilibria, we start off with the biggest K. And so this was just to determine which is step 1. Will Ka be step 1 or Kw be step 1? Sometimes, well actually, like 99% of the time, Ka is step 1. But 1% of the time, I'll give you one of these acids, one of these. 1% of the time, I'll give you an acid that really stinks, in the sense that its K value is really bad. How many bad acids do we have? I mean, bad acid means it's even worse than water. That is, these acids are less acidic than water. Well, is water very acidic? No, water is like neutral. And so if we have an acid that's worse than water, are there any on this chart? Yes. HS minus. HS minus is even worse than water. And so water is going to be step 1. HS minus would be step 2 if I gave you something like sodium hydrogen sulfide salt. Are there any others worse than water? Not on this chart, but on other charts there are. Okay. And so that's it. And then obviously if I have polyprotic acid, there's going to be K1, K2, K3, etc. What we think about, for each successive step. All right, so this is it's supposed to be 6.2. We get 6.14. It's a question mark. Is it round off or did I make a mistake?
Probably round.
It's probably round off, so we'll just say it's okay. If I got like 5.9, I'd really start to worry. If I got 5.9, I'd probably carry a whole bunch of extra digits just to make sure it's not round off. Okay, because 5.9, starting to drift. What about this? Let's just make sure that this equals 1.0 times 10 minus 14. This one I didn't carry that many digits either, but let's go ahead and do it. 101.09 times 10 to the minus 9. Times 9.89 times 10 to the minus 8. 9.89 times 10 to the, let's see, 3, 6, 9, 12, 13, 14. This comes out good. 1.00 times 10 to the minus 14. That's good. That's right on there, right? That's right on. So, what should we do next? We saw that the double check is good, right? The double check is good. And this is what we do in chapter 15. Chapter 15, we do this because we're only dealing with single equilibria. But when we start to deal with multiple equilibria, we have to do one more double check. You know what that one more double check involves? The one more double check involves this. When we do step 1, we get these values. But in step 2, since there's common species, that common species is changing, hydronium in this case. In fact, if we want to look at the hydronium is increasing. And so the double check here is this. The common species between all the equilibria should have the same concentration. If they don't have the same concentration, then Le Chatelier's perturbation is going to happen. And so what we do here is this. In order to maintain the equilibrium in step 1, the hydronium has to be 2.19 times 10 to the minus 9, or about that, right? Otherwise, there's going to be a kick. But what happened here? We started off with 2.19 times 10 to the minus 9, and then we add 98.9 times 10 to the minus 9. And so we add about like 99% more or something hydronium. And so what does Le Chatelier's principle say? Le Chatelier's principle says that if we take a system at equilibrium and increase the product concentration, this equilibrium should shift to the left. And so we need to fix that, because what I did was I added a tremendous amount of hydronium in step 2. Do you see that? It looks like a tremendous amount of hydronium was added in step 2 here. And what that's going to do is it's going to screw up step 1. Because I can't have two, this is the same solution. This is a mixture of HCN and water. I can't have two separate hydronium concentrations in the same beaker. Like, for example, I can't say, okay, half the water on this side maybe has this concentration of hydronium, and the other half of the water, maybe on the other side, has this concentration of hydronium. No, there's only one concentration of hydronium in this beaker, right? And which is it? Is it going to be this one that satisfies step 1, or is it going to be this one that satisfies step 2? Or neither. It's going to be neither of them. And so what we have to do is, I have to do Le Chatelet's perturbation. I started off at 2.19, now I'm at 101.09. And so the concentration of hydronium increased significantly, which is going to shift step 1 back to the left. But you can see we're going to run into a problem, because if we shift this one back to the left, that is, we start with 101.09 and then we lose some of that, then this concentration is going to go down, and that's going to shift this to the right. And so this is like an endless loop. It's an endless loop because you fix one and you screw up the other, and so you fix the other and you screw up that initial one. So no matter what, we aren't going to be able to solve this. We aren't going to be able to solve this in a stepwise fashion. You see that? This will perturb step 1. So even though they checked out, when we did the double check for the case, it's an impossible scenario because we can't have 2 separate concentrations of hydronium, one for equilibrium number 2, one for equilibrium number 1. This will perturb step 1. And unfortunately, we can't fix it by just redoing step 1, because if we redo step 1, it's going to screw up step 2. And we're in this endless loop. This is not possible to solve. Stepwise. Now, why didn't we end up with this endless loop in the last problem? We didn't end up in the endless loop in the last problem because the concentration didn't change much. I mean, the change in concentration in going from step 1 to step 2 to step 3 was negligible for the common ions. There are common ions in all the multiple equilibria. And so with all the common species between the multiple equilibria, their concentrations were consistent. In other words, the concentrations could simultaneously solve all of those. What about the HCl problem? Do you guys recall the HCl problem? We did something like this. The only difference was that we used HCl. And so the other example, but what about HCl? Do you remember HCl was 1.0 times 10 to the minus 8 molar HCl? And so we did the HCl. This gave us hydronium, Cl minus. So initial change in equilibrium. So at the equilibrium we had 0 molar, 1.0 times 10 to the minus 8 molar, 1.0 times 10 to the minus 8 molar. And then we looked, chloride's not going to be a hydronium producer. The only other hydronium ion producer would be water. We looked at water, H2O liquid plus H2O liquid. This gave us hydronium plus hydroxide. And here we take the common ion and bring it down. That would be 1.0 times 10 to the minus 8 molar here. Hydroxide 0 because we assumed that nothing has reacted yet. And then the change. And so at equilibrium, this is plus X molar. Tell me what it was at the end of this. Can somebody look? Did anybody write it down? What was the equilibrium concentration after step 2 in the HCl problem? It can't be 1.0 times 10 minus 8 because that would give us a pH of 8, which is basic. It had to be a little bit bigger.
About 10.5 times 10 to the negative
10.5 times 10 to the negative
8.
8. All right. Now, if you look at this, equilibrium 1 had 1 times 10 to the minus 8. And then step 2 screwed it up. And so we were good in step 1. But step 2 added about 90% more hydronium. And so if I look at this, you know, doesn't step 2 screw up step 1's equilibrium? Won't this perturb step 1? The answer is no. It doesn't perturb step 1 because the difference between this problem and that problem is HCl. HCl is a strong acid. And this would be the case. You know, if Le Chatelier's principle worked with the strong acid, then we should be able to neutralize the strong acid. That is, we should be able to raise the pH. That is, neutralize some of the hydronium by adding chloride. If we add chloride to this, right, it should shift it back to the left, thereby increasing the pH, right? And so, with sodium chloride, would adding sodium chloride to HCl neutralize the acid? No, it doesn't do anything. And so, because it's strong acids are one way. Strong acids aren't going to be perturbed by Le Chatelier's. In fact, chloride is too weak of a base to do anything. And so this is the difference. If this were a weak acid, then we're in trouble. If this were a weak acid, then we have an endless loop. That is, step 2 screws up step 1. You go back, fix step 1, and then you've just screwed up step 2. And so the answer is no, because step 1 is a strong acid, therefore it doesn't perturb it, therefore this works. And we got the pH of 6.9, whatever. Over here, step 2 really screwed up step 1. Even though this checks out, this checks out, they don't check out together. They have to check out simultaneously. If they don't check out simultaneously, they're in the same beaker, they're in the same water. There's only one hydronium ion concentration. We can't have two. And so how do we solve this? And so what we see is it's not possible to solve stepwise. So is there an alternate method that we could use to solve this? If stepwise fails, we have to use an alternate method. We must use something that I call simultaneous rather than stepwise. There are different methods for simultaneous that we can use. There's certain kind of algorithms and this kind of stuff. But the simultaneous method that I'll show you is that rather than solving one and then the next one, we have to solve them simultaneously as a system. In other words, we do this. So, for example, here, HCN plus H2O liquid is going to go to H3O plus cyanide. At the same time, we need to solve this. At
At the same time, we need to solve H2O liquid plus H2O liquid. This goes to hydronium plus hydroxide. So we set up the ice tables here. And we do this now. We have to think in terms of simultaneous. And so, actually, maybe I'll use the same symbols as our book uses for the setup, rather than doing it differently. Or maybe not. Yeah, maybe I will. I'll try to use the same symbols as the book. Or maybe not. So here, we're going to have the initial constant. Actually, I know what the initial concentration is. I'll just set it up generically first, and then we'll put in the numbers later. And so we have the initial concentration of the HCN, which we'll just call HCN initial. HCN initial is 1.0 times 10 to the minus 8. Water is pure liquid. Hydronium and cyanide, we assume that nothing's happened, but we have to assume that something's happened. And that something that's happened is this. You know, at the end of this, the total hydronium is, well, the two contributors to the total hydronium. And so one contributor is going to be the hydronium from this equilibrium. And so we'll call this the hydronium from the HCN. Plus, we're going to have another contributor with the hydronium. And the other contributor with the hydronium will be the hydronium from H2O, liquid. And so what we have to have is we have to have the same total hydronium on equilibrium in both of these. And so I know I'm going to have two here. I've got to make sure that I have the hydronium from the H2O plus the hydronium from the HCN. I'm going to do this differently than your book a little bit. And so the way we get that is we don't start off with 0 and 0. You know, normally when I do it stepwise, we just reset it and we start with 0 and 0. When we do simultaneous, we're going to do it a little differently, and this is where we're going to do it differently. When we're doing it simultaneous, we gotta imagine that there's already hydronium present in here for the HCN, and that hydronium, where did it come from? There's already hydronium present here, even though this HCN hasn't done anything, so there's no cyanide in there. But there's hydronium present. Where did that hydronium come from? Water. Okay. And so this is going to be minus X molar, plus X molar, plus X molar. And so we're going to get the HCN initial minus X. And then we're going to get the hydronium from water plus the hydronium from cyanide, HCN, hydrocyanic acid. And so this is the plus X here, although I wrote it backwards here. This would be the X. Do you see that? And normally I reset this and assume no water has done anything, which is fine. I'm going to reset this. However, there's going to be hydronium already present in the solution. Where did that hydronium come from? The hydronium that's already present in solution is going to be the hydronium that we generate from the HCN. And so there's already a common ion here. The hydronium from the HCN is going to be contributing to the water, and the hydronium from the water is going to be contributing to the HCN. The hydroxide is going to be 0 here. And so again, this is going to be, you know, plus, we'll just call it plus, should we call it plus Y? Let me see what they called it. plus y, I think. But they didn't set up the table. If they set up the table, I could see it quickly. I don't want to read this stuff. But yeah, self-ionization of water causes y. So this they call y. And so we'll call this y plus y here. So we'll end up with y molar here. We'll end up with x molar here. All right, now now you can see this. The hydronium from the water we call y, and the hydronium from the HCN we call x. And so at equilibrium, the hydronium concentration at equilibrium is going to be x plus y. That would be the hydronium from here. And then over here, the hydronium at equilibrium is going to be y plus x. Okay, they call the HA initial C. So our book calls this C. So our HA initial. And so let's go ahead and do these here, because if we call that C, this is going to be C minus X here. And C stands just for the concentration. And so what we need to do is we need to solve this system of equations. And this is going to be, this is like, you know, when we have two unknowns, we need two equations. So this is basically it. We have two unknowns. We have X as an unknown and Y as an unknown. And so the K here is going to be the hydronium ion concentration, which is X plus Y, times the cyanide concentration, which is X, divided by the HCN concentration, which is C minus X. This is the K for HCN, and this is going to equal 6.2 times 10 minus 10. And then over here we're going to have K for, in other words, KW. KW is going to be the hydronium ion concentration, Y plus X, or X plus Y, doesn't matter, times Y. Here. And this is going to equal 1.0 times 10 to the minus 14. Now you probably have done lots of two unknown, two equation type algebra problems, right? So you probably don't think much of them. They're probably pretty easy, right? Try this one. Okay, give this one a shot, and then let's see how the math looks.